We are going to be counting some more today, and we've got a bit of a new setup. This one is, it's a kind of telestrator. Been working on it. This is just this is just for the VOD. Nobody's tuned in yet. But you can see I've got a little dot here. I can draw things with. Of course, it's perfect freehand. Thank you, Steve. I've messed up all the settings to make them horrible. But I can, I can do all kinds of stuff now. I have complete control. But today we'll be counting. Today we'll be counting some more. We'll see how far we get. If I'm very good, we will get through all of this section, and then we will finally be proving things. Maybe we'll get there today. Okay. Counting subsets, section 3.5. The previous section dealt with counting lists made by selecting k entries from a set of n elements. We now turn to a related question. How many subsets can be made by selecting k elements from a set with n elements? Okay, k element, what's this? K elements from a set with n elements. How many subsets can be... Okay, this is different. Selecting k entries from elements, and now it's, okay, how many subsets can be made by selecting k elements from a set with n elements? Okay, seems pretty closely related. To see the difference between these two problems, take A being this set here, and consider the non-repetitive lists made from selecting two elements from A. Fact 3.4 says that there are 3.4, that must be the, what's fact 3.4? Oh, K permutation, which we also denote as P. Hello, lovely talent. Hello, lovely Terran. Good username. I am learning shit. That's what I'm doing. I'm learning to count. I'm learning some high level, well, medium level counting. Okay, we've got a P there. Can it? It is math. It is indeed math. We're on the way to reading and any percenting the whole of Donald Knuth's The Art of Computer Programming. And this is a prerequisite. Well, for me it's a prerequisite because I don't know proving things, and this is called Book of Proof, so I'm learning to prove things. Okay. So P, this thing is, what is this again? I've just forgotten. It's this. It's a K permutation, which is... A K permutation of an element set is a non-repetitive length K list made from elements of the set. So it's like... It's an arrangement of Ks... Arrangement of K of the set's elements in a row. So we care about order there as well, because it's permutation, I guess. Game development and coding gives me good feelings always, but too lazy. What kind of feelings does it give you? Okay. Consider the non-repetitive lists made from selecting two elements from A. Yep, fine. These lists. But there are only 10 two-element subsets of A. Oh, because of the repetition, basically. Yeah, we get A, B here, and then we've got, well, we should have a BA somewhere. Here. So we've got A and BA. A, B, BA, but we've only got one here. Hence there being 10 versus 20. Okay. The reason there are more lists than subsets is that changing the order of the entries of a set produces a different list, but changing the order of the elements of a set does not change the set. Using elements A, B in A, we can make two lists, A, B, and BA, but only one subset. Makes sense? This section is concerned with counting subsets, not lists. As noted above, the basic question is this: how many subsets can be made by choosing k elements from an n element list? So this seems like it must be similar to filtering the power set based on the length of the set. So I think in builder notation, this is one I struggle with. Okay, 2. No, that's the other one. Yes, 2. Okay. So this is, let's say, x in the fancy p. See if I can draw a fancy p. In the power set of, let's say, x. This is terrible notation. Where the cardinality of x is equal to, let's say, 2. Right, and then it's this symbol. Hello, Bobladon. Oh, you woke up from a big old nap. How big was the nap? How discombobulated are you feeling? I always feel very dazed after napping, but maybe you don't. Okay, so I think that's equivalent to what we've learned before. But here we're counting. Here we're concerned with, like, I guess the cardinality of this set, right? That's what our question is here. Not just listing the sets out, but counting the number of sets in the power set where the cardinality is 2, I think. Happy Nora, straight in with the criticism of the fancy P. I'm sorry. Yeah, okay. Alright, the P's not fancy now. Let me try to draw another one. No, that's even worse. That's terrible. Okay, Bobadon's saying this notation is a little inaccurate. It should be x in px before the colon. Yeah, my notation is I thought the colon was like in, I thought the colon, I don't think I've seen in the notation I've been learning anyway. Maybe I'm sure there's different notations. Bob, you have been discombobulated. You've been so tired this week because of the temperature. Oh, yeah. Yeah. I've also been affected by the temperature in Western Europe. I'm being affected by the temperature in Western Europe right now, in fact. Very sad. Oh, yeah. It's the element symbol. Oh, yeah. Oh, yeah. I get you. Let's see if I can remember how to erase things. Okay. Yeah, it's this, right? It's that symbol. That's the one I mean. And then it's the colon. Yeah, you're right. Wow, obviously you're right, but now I see how you're right. Okay, great. Okay, that's right. I wanted to get into the comma again, obviously. Oh, I've done it the wrong way around. Oh no. Oh no. I was sure. I was sure that time because I was like, well, this looks kind of like an E, so it can't be that, but it is obviously because it. My memory works in horrendous ways. Terrible. Yeah. Okay. Thank you, everyone. Thank you, everyone. It's very similar to being tutored, but tutored by like 8 different tutors at once. Oh yeah, true. Yeah, Happy Nora, you're right. Subset of, that's true. Yeah, because I guess the subset of constructs the power set, right? Hello, in a climb bottle. Greetings to you too. Can we get a temperature check? What temperature is it where you are? Without doxing yourself, in case if you're in a very specific location where the temperature is very unusual. Maybe round it. Maybe add or subtract a random number within the range of 1 and 0. Okay, temperature here is 27 degrees. I want to know what the temperature is where you are. The element of symbol was thought of by Giuseppe Peano, of Peano. I never pronounced that out loud before. Peano arithmetic, right? I suppose. At the end of the 19th century, to represent the Latin verb est. So it's a little epsilon. Huh. There you go. There you go. All right, I'm back in. I'm going back to the. I'm back in the book. If you have challenging questions for me, please retain them. I will engage with them. I will engage with them later. Okay, where are we at? Yes. So basically, the thing I was thinking was this whole question about counting that we're on kind of feels similar to the power set. Like he hasn't mentioned the power set yet, so maybe it's different. But okay, this section is concerned with counting subsets, not lists. As noted above, how many subsets can be made by choosing k elements from an n element set? Oh, and I missed someone's message actually. Now I think of it, there was something I meant to reply to. Tikali, you've been following the YouTube VODs. Welcome to the live experience. Thanks for following along. Okay, how many subs? Yeah, great. Okay, definition 3.2. If n and k are integers, then yeah, okay, I've seen this notation before. It's these big brackets, n and k. Yeah, I did this at school. Denotes the number of subsets that can be made by choosing. Oh, it's choose. It's choose. K elements from an n element set. We would read nk as n choose k. Some textbooks write cnk. I've seen, I think at school I was taught n big C k. They taught me that instead of this. Well, anyway. Piano. Okay. Piano. Got it. Okay. Usually the N is superscript, huh? Well, in a climb bottle, it's 29 where you are. That sounds diabolical. It got up to like 32 here earlier this week. It's not streaming weather, I'll tell you that. Yeah. Will I survive long? I hope so. I have a fan which will hopefully not interfere with the microphone too much. I am UK based. Yep. I lived in London for some time and then I got priced out. But I'm still in the UK. Sticking it out. This is illustrated in the following table that tallies the k element subsets of the. Oh no! See, I gotta erase some stuff now. Tallies the k element subsets of the 4-element set A, B, C, D. We're familiar with that set for various values of k. Okay, that's minus 1. Okay, great. We're starting off strong. Minus 1. 4 choose minus 1 is 0. I guess this will become important later if we start doing induction, right? Maybe? I don't know. Choose 0 is the empty set. I guess these are going to be true whatever the set is. K choose 1 is going to be... Just make sure my microphone is not doing anything weird. Okay, don't think it is. K choose 2, yeah, K choose 3, K choose 4, K choose 5 is empty. Okay, that makes sense. Intuitive. Yeah, long enough to get through these books, hopefully. Yeah. Hello, Naimir. Hello, welcome back. Bobbledon, is this your own whiteboard now? It is. It is. I've been playing around with. I've been building my own again. My friend called me. My friend used to work for TL Draw, and I said, you know what? I've been building my own whiteboard, and she was just like, oh, she just sighed. Horrendous. Worst habit, building your own. But cool thing about it is it's got transparency, so you can put it on top of anything, including me. You can put it, just draw all over here. And it does use Steve of TL Draw's perfect freehand, but I've mutilated it so that it simplifies the paths a bit, because it makes my handwriting slightly better. Yeah. If I had the technology to make the lines thicker at this point, that'd be better. Okay. All right. So we got some subsets. Fine. The values that appear in maybe he's not mentioning the power set because he's not assuming people have been through that section. The values of k appear in the far left column of the table. Okay, fine. Fine. We'll go back up. Okay, that's not very helpful. Yeah, it sounds pretty straightforward. To the right of each k are all the sub. Yeah, we get how the diagram works, Richard. Yeah. Okay. Okay. When k is equal to 0, there's only one subset of A that has cardinality k, namely the empty set. Fine. Notice that if k is negative or greater than the cardinality of A, then put these rain noises back up. Greater than, yeah, then A has no subsets of cardinality k, so that's 0. Okay. In general, n choose k is 0 whenever k is less than 0 or k is greater than n. In particular, this means n choose k is 0 if n is negative. Makes sense. The Soviet notation for this, says Naimir, is C, K, N. Right. Cool. Thanks for sharing that. That's cool. I like that. Alpha Victor Charlie says there's a decent amount of lag between video and audio. The audio lags behind the video. Unfortunate. Okay. Wet says no audio desync. Less than half a second, says Bubbledom. Okay. How's the temperature of my laptop doing? 71 degrees. That seems okay. Hopefully it resyncs soon. I have no debugging tools to get rid of that. Now you should know how bad the desync is. Everyone should know at that point. Okay. Yeah, makes sense. Negative K. Although it was not hard to work out the values of 4 choose K by writing out subsets in the above table, the method of actually listing sets would not be practical for computing when N and K are large. We need a formula to find one. We will now carefully work out the value of 5 choose 3 in a way that highlights a pattern that points the way to a formula for N choose K. Ah, it's better now. Thank you. Let me know if it gets worse again. And I'll try and move my lips a half second later than I talk. That would be interesting. That'd be an interesting challenge. To begin, note that 5 choose 3 is a number of 3-element subsets of this. These are listed in the top row of the table below. Okay, let's look at this table. Where we see 5 choose 3 equals 10. Okay, that's this part, I suppose. The column under each subset tallies the 3 factorial equals 6 permutations of that subset. Okay, that's the permutations. The first subset has, yeah, okay. Yeah. The ventriloquy, I don't think I've ever said that word before. Ventriloquy. Try saying it. Try saying it with a slight delay on your audio. Yeah, sometimes if you're traveling through the UK, do you get this in other countries as well? You see in the windows cardboard cutouts of usually meme people. Imagine being a meme person, a terrible fate, or celebrities. Maybe I'll get one so that people can put me in their window. I don't think that would be a good idea at all, but it will be funny. Okay, body of this table has, okay, fine. Yeah, we get the idea. Notice that the table consists of every 3 permutation. Fact 3.4 says that there are, what is this called again? Always forgetting fact 3.4. Gosh, that's annoying. Fact 3.4. K permutations. I should know that. Remember, it's K permutations. K because I'm K, and P because it's a P, so it's just permutations. That's how you remember that. Yep, okay. There are... this is K permutations equals 5 factorial over 5 minus 3, such 3 permutations. Okay, great. Thus, the total number of lists on the table can be written as either 3 factorial 5 choose 3 or 5 factorial over 5 minus 3. Okay, he's doing something. I don't know where he's going. Where is he going with this? He's just saying, this is interesting so far. He might name it at some point. Working this out, you'll find... Wait, okay. Which is to say, 3 factorial 5 choose 3 is, okay, fine. Dividing by both sides by 3 factorial yields 5 choose 3 equals 5 factorial over 3 factorial multiplied by 5 minus 3 factorial. Fine. Dividing both sides by 3 factorial. Oh, right. So he just wants to get rid of this so that he can have a formula for this. Okay, that's where he's going. He's trying to get a formula for n choose k. Fine. Okay. Okay, fine, fine. But there was nothing special about the values 5 and 3. Whoa! We could do the above analysis for n choose k. I should be less bratty towards Richard. He's just trying to help me understand. We could do the above analysis for n choose k instead of 5 choose 3. The table would have n choose k columns and k factorial rows. Okay, fine. Yeah. It's a fact. He's established a fact. Great. It's this fact. This is the fact. Fact established. If k is between 0 and n inclusive, then n choose k is equal to this formula. Otherwise, it's 0. Let's now use our new knowledge to work some exercises. Great. Bobdadon, you're full of new words today. Obstreperous. Obstreperous. Is that a real word? Obviously it's a real word. Okay. What does my computer say about what that word means? Noisy and difficult to control. I suppose. Yeah. I feel like this. I'm regressing to school attitude now. Yeah, I know. Okay, where are we? How many size subsets does this have? Fine. So let me, now I've got the formula off my screen. Let me get rid of all this. Let me see if I can remember it. Whoa, okay. N choose k is equal to forgotten it already. N, because n is all the permutations, right? And then it's, I think, is it this? I've been doing this a lot lately with the quadratic formula as a way to test this software. But this will be my new one. Now that doesn't look right at all. Let me find out. No, almost though. Almost. This n is wrong. And then it's right. Boblidon's commenting on, you've managed to make it so you now have to erase the whiteboard as well. That was indeed my objective. My model for this software is the class whiteboard, you know, like a lecture theatre whiteboard. I've tried to make it as much like that as possible within the constraints of software. and the erasing is kind of part of it. There is a reset tool, but and I'm still not 100% happy with how erasing works, but there are some trade-offs there. Hence the chalk colours also. Okay. These I sampled from a real chalk. Well, those are pretty similar. So many bugs. Something like that. I should make it so the pen runs out. No, I should make it like it very slowly fades away, like a whiteboard pen. That would be that would be like my school experience, where the teacher just comes in and none of all the pens are like invisible, but they persist anyway. And then they, that was so good. They should do a meme about this. The feeling when like the teacher picks up like the pen starts working like for the 8th time, and they pick up a new pen, and it's just like, it's so perfect. It's like bold. It's the perfect color. It's just so that was a satisfying moment for me anyway. Okay. Yeah, we got that. We got this. K on the... Okay. We got... Okay, let me try and inject a few things about this in my mind. So we've got all... What colour am I on? Okay. We've got all of the permutations on the top here. So there's only one term, and it's all the permutations. But then we cut down the number of permutations by this term. And this term is... I think this part does the job of dividing out all of the permutations that are not that are larger than the right size. So if we were going for like n choose, like if we were going for like 8 choose 3, n minus k divides out all of the ones that would be of length 4, 5, 6, 7, and 8. So that's what this one's doing. And so this one feels like intuitive to me. In which case, I guess this term here must be doing the job of dividing out all of the different arrangements of 3 elements, which makes sense because we know that k factorial will be all of the arrangements of k elements, all the permutations of k elements. So we're dividing out that as well. So we would never have k on the top here because it's just not relevant, not important. We can use different colors. At some point I'm going to make this more interactive as well, so you will be able in some way to draw on this board, but in a very constrained way, obviously. Not that I don't trust any of you here, but okay, that reasoning is exactly right. Okay, brilliant, thank you. I always thought it was kind of crazy that this division always yields an integer. Yeah, I guess it is. Cool. Somebody should prove that. Probably they have. All right, so we got this another example. Is there anything funny about this example? I don't think so. Just going to skip through that for time. Somebody's got some cards here. That's very exciting. A single 5-card hand is dealt for a standard 52-card deck. how many different 5-card hands are possible. So in that case, we're looking at 52 choose 5, right? Which is indeed what is being done. And then that's just calculated, right? That's fine. This problem concerns 5-card hands that can be dealt off a 52-card deck. How many hands are there in which 2 of the cards are clubs and 3 are hearts? This seems more challenging. Let's give this one a go. Let's see if we can learn anything about this. Okay. How many cards are there in which 2 of the cards are clubs and 3 are hearts? How are we going to work that out? What comes to me immediately is nothing to do with choosing at all. So I'll just follow my intuition and see where I get stuck, and then I'll probably refer to the explanation. So if we've got like 52 cards, and we've got 4 suits, which is going to be 13 cards. Every time we pick a card, I'm steering into probability here, which is not where I want to be. Okay, so each time we could pick one of 4. We've got four choices. If we're just ignoring the cards themselves and thinking about the suits only. Wow, my intuition is not taking me anywhere with this question. Let me think about it differently. Let's try and simplify it. Let's say we've got wow, nothing at all. Okay, let me read a little ahead and see if I get any hints. Where the first entry is such a hand is described by a list of length 2 of the form this. Okay, we could describe it like that, I suppose. Where the first entry is a 2-element subset of the set of 13 club cards. Right. Okay, so there's one way we could do this then, that occurs to me. So we could do 52. Wow, terrible numbering there. Let me do that again. 52, choose 5. And this is the total number of possible hands. And then we could work out how many times can we do 52 choose. I know you're giving me hints in the chat. I'm not looking at them, but thank you. A 52 choose... Well, I actually don't know you are. You might not be. You might just be hating. I'm sure you're not. A 52 choose 2, where... no, I'm getting nothing. Getting nothing. Why is this confusing me so much? How interesting. My brain's just slow today, or is it an unusual question? I don't have a recipe for it in my head. The second entry is a 3-element subset of the set. Okay, so where the first entry is a 2-element subset of the set of 13 club cards, and the second entry is a 3-element subset of the set of 13 club cards. Heart cards. There are 13 choose 2 choices for the first entry and 13 choose 3 choices for the second. So by the multiplication principle, there are 13 choose 2 by 13 choose 3 such lists. If we were choosing... Wow, that's just the end. It's just the end. Is that it? Wow, does not seem that does not seem like it should be it. You know what I think it is? I think I'm getting pulled in. I'm getting pulled in by the notion of trying to work out the probability of that happening. That's what I'm really getting pulled in by. That's why it feels like that can't be the answer, because I'm not thinking about counting, I'm thinking about what's the probability of it, which is not the question at all. So if we had a deck of cards and we could look at every card like they're all face up, the question is, if they're all face up, how many different hands, because it's the hands that's confusing me, because I'm thinking of like the chance in like a poker or whatever. If we had all of the cards face up, how many possible hands could we make based on just picking the cards as we liked, really? Nothing's preventing us from picking them. The question is counting them. That's what's troubling me on that one. So given that, we don't even need to worry about the other 2 suits. Like, we can just throw those away because we don't care about them. We're only choosing, and if we were doing this for real, we would just put the clubs in one section and the hearts in the other, and we just pick from them, right? Yeah, so I'm just being pulled in the wrong direction for this. Okay, interesting. I won't work it out because there's no point now, but interesting. Okay, what's chat saying? Rain intensifies. Yeah. Thunder and lightning today. We got some thunder and lightning yesterday, actually, where I am. Redeeming a miasma of death and disease for channel points. Wow. The probability of it happening is always the amount of hands divided by 5 factorial. True, yeah. Inner Climbot says, yes, this is the correct logic. The probabilities drawing such a combination will be the number divided by all possible 5-card draws. Yeah. Interesting. My intuition will have to mature on this. Okay, example 3.15. A lottery features a bucket of 36 balls numbered 1 through 36. 6 balls will be drawn randomly. For $1, you can buy a ticket with 6 blanks. You fill in the blanks with 6 different numbers between 1 and 36. You win $1 million if you choose the same numbers that are drawn, regardless of order. What are your chances of winning? Well, this one, even though it is about probability, in this case, feels more obvious. Let me see if I can convert feels obvious into a correct answer. Okay, 36. Choose 6. And then it'll be 1 over that, right? Let's put a little hat on it. I think. And let me work out 36 choose 6 just to get my memory on this. Okay, so it's n factorial over 6 factorial multiplied by n, what? That's 36 minus 6 factorial. Let's see if Python will play ball today. So let's try and do this in one. Well, actually, let's see it. Let's just look at it. Wait, actually, do I just have factorial now? No. Let's just look at it. Oh, such a large number. Delightful. Math factorial 6 multiplied by 36 minus 6. That. Okay, so we've got 1, 9, 4, 7, 7, 9, 2. Which is not 6 digits, because if it was, I would choose that number. Okay, and that is the correct answer. Great. Let's get some color back in here. Okay, good. Oh yeah, I got to float. I got to float again. The book may cover arrangements. Oh, permutation, is that the same thing? I suppose it is. Yeah, if it is permutations, it was covered covered in the last session, I think. And the notation you're talking about, which is A. Is it? Do you mean like this, or is it this? I guess it probably is the first one. Not familiar with that arrangement, that notation. Okay, I will redo this with a double, so that we don't have floating point numbers on the screen. Terrible. We don't want that. Did you know that John Backus's speed coding system uses essentially the same floating point system as JavaScript does today? I just assumed it would be different. I don't know how it'd be different, but yeah. Well, not exactly that. I actually don't know if it was standardized. It probably wasn't standardized at that time. IEEE 754. Yeah, something quite similar to that. Nim is saying it's the number of ways to select and arrange k distinct elements from a set of n distinct elements. I think that's the same. That's the same thing as in this book. I think it's k permutations, which is notated as. I think it's this. Which actually I don't like as a notation, so I prefer yours. Yeah, Bacchus predates IEEE 754. It makes sense. Did you know? I learned an interesting fact about John Bacchus yesterday, which is that I think at some point he maybe in one of the world wars, I guess the second, he had a skull injury, and they put a metal plate in his head. This is before he was a software engineer, by the way, before he was a programmer, I suppose. And he didn't. He felt it was not quite right. He felt it was a little looser than what he would want it to be, and so he just designed his own. He got someone to fit it for him. Interesting guy. He was doing a medical degree, I think, because he did well on a medical aptitude test when he was in the army or something like that. Real interesting anecdote, that one. Okay, binary strings have an odd number of ones. Okay, this one seems not obvious to me. Okay, how many 7-digit binary strings? Now that will be... Uh, 2 to the 7, right? Or is that wrong? Yes. Is that just the number it can... Is that just the number it can represent? In theory, there should be one arrangement for every number in that range. Or is it 2 to the 8 minus 1? Let me do this another way and work this out. No, it'll be 2 to the 7. 100% it will, because we've got, if it's 1 digit, it's 2, which is 2 to the 1. If it's 2 digits, it's 2 to the 2, and that'll be 4 arrangement. Yeah, okay. I don't know if that's how I'm supposed to work it out, but... Okay, so that's the total number. And how many 7-digit binary strings have an odd number of ones? Okay, so the odd numbers in that range will be 1, 3, 5, and I guess 7. Now, for 7, there's only one possibility, which is 1, 1, 1, 1, 1, 1, 1. For 5, I'm struggling with the idea that we don't know. We do know the total number of ones that we have to select. I guess you know what it is. It'll be the permutations of. No, that doesn't make sense. I was thinking it could be the permutations of, like, this string, but that's not right because all the permutations of this are identical for our purposes. So again, wow, my intuition is not helping me at all. Okay, let's look at this one. So here we could have 0, 0, 0, 0, 0, 0, 1. Or we could put this 1 in any of these positions. So there's going to be 7 possibilities here. Now, what does that relate to? And then we've got 1 possibility here. I mean, this would be the same as 7, choose 1. And this will be the same as 7. I'm just noticing this. I don't know exactly why this is yet. 7, choose 7. So, you know, following the pattern, we would expect this to be 7, choose 3. And this to be 7, choose 5. And then we get all of the different possibilities. So if we add all those up, we should get the right number. Now, why is that? 7, choose 3 ones? No, it doesn't seem right. It doesn't. I mean, it seems right, but it doesn't make sense to me. All right, let's find out what the actual answer is, and then we can build my intuition on why that's true. No, it'll be, do we have choose here? Or choice? No. All right. Let's just take this as summed, and we'll see if the answer is something like this. Okay. Let A be the set of all 7-digit binary strings with an odd number of ones, so the answer will be cardinality of A. To find cardinality of A, we break A into smaller parts. That's the addition principle we saw before, right? Notice any string in A will have either 1, 3, 5, or 7 ones. Let A1 be the set of 7-digit binary strings with only one. Yep, fine. So we're indexing the sets. Yep. And we union them, so we add them. Now we must compute the individual terms of this sum. Take A3, the set of 7-digit binary strings with 3 ones. Such a string can be formed by selecting 3 out of the 7 positions. You know, something my brain was saying it was something to do with positions. I don't know why I didn't follow that. 3 out of the 7 positions for the ones and putting zeros in the other. Okay, so we're selecting and let's call this 1, 2, 3, 4, 5, 6. Wow, terrible. And 7. Okay, and so we're selecting, we're choosing 3 of these positions and putting ones in them. So then we've got how many different ways are there to choose from 7 possibilities, that's the position, 3 of them. Okay, that makes sense. So we're choosing positions in this case. Okay, so we get that, and then we add them together. 64, fine, well, I believe that. Okay. You're choosing, so name it, that many zeros to replace with ones. Makes sense? In a Kleinbot says, if you think of it like this, each binary string defines a subset of a set with 7 elements by selecting the elements whose positions correspond to a 1. Then you look at the combinations. Oh, it's math.com, I see. Now suppose you swap all the zeros and ones. What do you observe? I guess we've got two other. We've got 0, 2, 4, and 6. This kind of seems like it should be the opposite, right? Okay. Right, now we've got some exercises. I should probably do these, given... where am I typing? Nope. Nope. Okay. Need to work on my software. No. There we go. Okay, need to change the foreground color. Right. Okay. Suppose a set A has 37 elements. How many subsets of A does 10 elements? How many subsets of A have 10 elements? How many subsets have 30 elements? How many have 0 elements? Okay, so for this one, we are going to be looking at... Come on. We're going to be looking at... Okay. It'll be 37... No, wait. How many subsets of A have 10? Okay, no, it is. It is. So it'll be 37, choose 10, or 30, or 0. Let's call that one. Or, yeah, basically that. So with 0 elements, well, actually, well, I guess I'll just work this one out. That's fine. I'll work it out, given we may as well get some practice in it. So this is going to be 37 factorial over... Oh, okay. 10 factorial multiplied by 37 minus 10 factorial, which we'll just work out this one. Won't do all of them. Wow, my laptop is really not happy. It's too warm for it. We've got, yeah. Whoops. Okay. 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 Oops, sorry. Got the slashes wrong again. Okay, is that right? Okay, fine. Let's have that be my numeric answer for that. That's going to be 3, 4, 8, 3, 3, 0, 1, 3, 6. Need to work on my handwriting in this system. Okay, now how many have 0 elements? That's going to be 0. No, 1. Got to get that one right. 1, the empty set. Okay, let's do the odd number ones. Okay, is there anything I can do with my computer to cool it down right now? open the most intensive system on my computer, which is the activity monitor. Okay. Maybe I can just sort this out. Okay. That's slightly better. And then close this and just close this other tab as well. Okay. Right. Are you running a local LLM? That is rough. You'll need to pay Anthropic more money instead, I think. Or OpenAI, depending on your persuasion. Or somebody else. Other AIs are available. Okay. 3. A set X has exactly 56 subsets with 3 elements. A set X has exactly 56 subsets with 3 elements. Okay, so we're saying that something, choose 3, is equal to 56. This should be relatively straightforward once we've got there. Now, let's expand this out. We should have n factorial over 3 factorial n minus 3 factorial equals 56. What can we do? We can multiply by 3 factorial, right? And 3 factorial is 3 times 2 times 1, so that's 6. And then we get to, we get to n over n factorial over n minus 3 factorial would equal, what's 56 over 3? Oh, that doesn't sound good. 18.6. No, sorry, divided by 6. That's 9 point... That's even worse. 9.3. Let's just keep it in some sort of form, I suppose. Maybe I'm wrong about this. Well, let's make this 6. And then this we can also replace with 6. And then I don't know what to do. Oh yeah, true. Good point. Dexter, hello. I did make a video on Ed. I did not divide both sides by 6. Oh yeah, I multiplied them by 6, didn't I? True. Good point. Yeah. So what we're actually doing, what we're actually looking for is this over, oh, that's too big, n minus 3 brackets, ooh, terrible brackets, factorial, and then it's, ugh, oh gosh, okay, 56 multiplied by 6, 336. There's probably something I can do, well, there must be something I can do with the left. I'm just thinking, so if we were to expand this, what we end up with is, we end up with, so this is going to be like n times n minus 1 times n minus 2. In fact, I think that probably is it. But it would continue, right? And then we're dividing it over, you know, that subtracted. So I think what we end up with is, yeah, because we're dividing by everything from n minus 3 downwards. So I think we can just get rid of that. And then I think we end up with this. I might be slightly wrong here, but I feel reasonably sure this is the right idea. I'm just saying there's no analytical way of solving this, I think. Robledon says, I think a good observation to start is that the left-hand side is a product of 3 roughly equally sized numbers. I suppose so. It's not just any cubic equation. Okay. So, well, we probably just, yeah, we could just probably figure this out, right? It'll be close to, it'll be approximately n cubed, right? So we could look for n cubes that are close to this. Do we have this? We have to do this here, or do we have something? I forget which language is like that. No, it's JavaScript that's like that. Not quite. Okay, that looks about right. So it would be, if it was 7, we'd have 7 by 7 minus 1 by 7 minus 2 to 10. Not quite right. Should we try 8? Great. Looks like it's 8. Eight. Okay, interesting. Thanks for the tips, everyone. Right. What are we on? 3. Let's look at 5. How many 16-digit binary strings contain exactly 7 ones? Now, we looked at something like this before, right? And it looks pretty similarly shaped. So we've got 16 positions, and we want to choose 7 places for the ones, right? So we've got 16, choose 7, probably. What a beautiful 8. Thank you. Thank you. I'll put that 8 back on the screen. Yeah. You know what? The thing that gives me the ick is seeing someone with an upside down 8. Like it's bigger on the top. Terrible. Okay. No, that's not 3. Why have I put 3 there? Wow, I am. It's hot today. Channeling that guy from The Simpsons. Seven. We've got some notation here. The cardinality of the set where X is an element of the power set of this set of 10 digits, 10 symbols that just happen to look like digits, where the cardinality of X is less than 4. I suppose if we were doing the even ones, that would be, we'd have already worked out the cardinality of exactly 4. We can use the addition principle for this. So let's do that. So we're going to work out the cardinality for 0, 1, 2, and 3. And that will be, we've got 10 digits there, so it's going to be 10, choose, let's go 3. Yeah, we'll have those sets in there. And then we'll just do a little dot, dot, dot. Ten, choose 0. Yeah, I think so. It is. I'm excited for it to get cooler. Again, always excited for change. Okay, we got the 8, we got 9. This problem concerns lists of length 6 made from the letters A, B, C, D, E, F without repetition. How many such lists have the property that D occurs before the A? Okay, interesting. So for this one, list of length 6 made from the letters A, B, C, D, E, F. So we could work out D occurs before the A. So we could like enumerate all the lists possible where D occurs before the A. And then we could work out how to count those. Now those would look like with the D first, and then it would be, we'd have some here, or we'd have and this would be non-Ds, crucially. Or we could have, no, in fact, let me make this a little bit more. 3, 4, 5. And then at this point, this would be a set, this would be for a set of 5 symbols. It's always actually going to be 5 because we know the D's in there. Or we could have one blank space, which could have one of 5 symbols in. No. And then a D. That's not a great D. And then 1, 2, 3, 4, 5, 6. And then here we could have one of 4 symbols in. And then we could do the same for the D being here, and the D being here, and the D being here. And then we couldn't ever have it here. Or actually, no, for here it would have to have the... for here it would have to have the... the A at this point. So that one would be special. No, actually that wouldn't even work, because if we had, let's say if we get rid of this, let's say if we had the D here, in that case we'd need to make sure that we had an A in one of these 2 positions. And we wouldn't have an easy way to do that. So I don't think this way is going to work. Introduce something else. We could try and do it with positions, maybe. Maybe that would work. We could choose 2 digits. So we've got 6 digits and we want to choose 2, and we know they're not going to be the same. If we choose 2 digits, let's say we choose 2 and 3. And let's say we have a rule, we always put the D on the lowest of these 2, because it'll be a set, so we won't care too much about that. And then this would represent this sequence. Ooh. So this would help us then work out how many different positions of DNA we can have. And then we just need to multiply this by the number of permutations of the other 4 characters, which will be the same because we're going to have DNA in general. So let's figure that out. So for the 4 other characters, let's call that let's give a number for that. Let's call this, I don't know, G. Let's choose a letter. So that's going to be 4 factorial, right? It's just going to be 4 factorial. Because we're just looking at arrangements of permutations of 4 symbols across 4 places. So we're not dividing anything out, and so we don't need to worry. So that'll be that. And then the other side of it is going to be the number of positions that we can have DNA. Let's call that B, I don't know. It's probably the right letter to choose. A right letter to choose, rather. And that's going to be 6 possible positions. Choose 2. That'll be the number of positions we can have. We don't need to worry about order in this case, I don't think. So I think the answer will be 6, choose 2, multiplied by 4 factorial. Okay, interesting. Go Noob 42, you're working through Book of Proof right now as well. That is cool. That is cool. I'm the briefcase says, did you see the new James Bond game? What an unusual question. Apparently it makes one of the most boring parts of video games fun. Why'd you ask? No, I hadn't seen it. Haven't seen it. Okay, final answer. Alright, 11. How many positive 10-digit numbers contain no zeros and exactly 3 sixes? Now, in that case, so no zeros. Let's say if we just wanted to work out no zeros, we could have the permutation. No, wait. If we just wanted to work it out with no zeros, I swear these problems were easier last week. How many positive 10-digit numbers contain no zeros? Okay, so if we had that, let's say we have a set of the digits 1 to 9. But we're going to have a repeat. That's what's tripping me up. Yeah, we're going to have a repeat in there. So we're going to have to use a slightly different method, I think. So if we had, if we were thinking about this as we did last week, first we could choose the position of the 3 sixes, which we could say could be calculated by having So it's 10 digits, so 10 positions. And then we can choose 3 of them. To choose the positions of the 6s, that would leave us with 7 other digits. And the 7 digits, that's going to be... so we've got 7 other digits, and they cannot be 6, and they cannot be 0. So that's going to be 8 possibilities. Yeah, so we've got 10 digits. 9 without the 0, 8 without the... yeah. So it's going to be 8 to the power of 7. Yeah, because we're choosing... Yeah, that's... I think that's right. No zeros, so we don't need to worry about that. Yeah. Okay. So that's 11. Let's look at 13. Want some more rain noise. There we go. Okay, let's look at 13. 13. Suppose that n and k are in the integers, and k is between 0 and n inclusive. Use fact 3.5, the formula n choose k equals etc., to show that n choose k is equal to... Okay, it's just got louder again. Okay, too much rain, too much rain, too much rain. Okay. To show that n choose k is n choose n minus k. Okay, interesting. I sense I'm going to have to do some arranging again. Oh, it's really rainy. Right. Oh, so it's basically just asking us to prove that, or not prove, but to show that something like, let's say we had 5 choose 2. This is going to be equal to 5 choose 3. Now I seem to remember there's some like triangle-y distribution of these chooses. So there's 1 5 choose 5. There's so many 5 choose 3. Sorry, 5 choose 4. There's so many 5 choose 3. There's so many 5 choose 2. There's so many 5 choose 1. There's 1 5 choose 0. So there's that sort of relationship here. I seem to remember that that's true. I suppose it's asking us to show that in some way. Okay. Let's try this out. Slightly out of my comfort zone on this. So we know the top's going to be the same regardless, because that's affected only by n. And we want to somehow show that... Okay, actually maybe this is... Maybe we could just substitute this in. The fact they've chosen k is not going to make things easy, is it? Okay. Well, let's write this out anyway. Okay, so we've got n in here, and we're going to have k n minus k. Right, and now if we substitute these in, if we substitute in this n minus k for k, what do we get? What do we end up with? And in fact, let's even get rid of this, right? We know that this is going to be here, so hopefully we don't need to worry about that. But we're going to try and just deal with the bottom half. Okay, so if k is n minus k, then what we end up with is n minus k. So it already looks great. Here's where it goes wrong, right? Or right, wrong. Now this is going to have n minus k. Minus k. So we need this to end up being k, maybe. Which it looks like it probably will, maybe. We don't need these brackets. Sorry, I've messed that up. I've done that wrong. I'm sure you're maybe saying that in the chat right now. Okay. Where were we? Where's my colors? That's right. So it's actually n. I substituted the wrong thing, as you probably realized. N minus n minus k. Now that looks more promising, because n minus n gets taken out. And we got minus k in there. Well, we can take the n's out anyway. And then we've got minus k factorial. So this ends up getting rearranged to maybe this minus k is some sort of problem. Brackets matter now, they're saying brackets matter now. Okay, let me try this again. Nope. Okay. Oh. Hi, good morning, and Stucky. How goes the art? The art is I'm getting to the art. You know, I learned something. I realized something. Somebody, after all of this dealing with induction, which I found a little challenging when we were working through Knuth's book, I saw a random Reddit post about someone complaining about induction, and I was like, wait, that makes perfect sense. So now I feel like I got it. I got it in that second when I wasn't actually doing any work. So I think it's going well. Okay. All right, where are we at? How's it going with you and Stucky? It's n sucky, actually. I apologise. Okay. Right, so with this, I mean, the brackets do matter here, you're right. So with this, we can change this to n plus -1 by, I think you can do this. It's been a while. It's been a while since I've had to do any of this. Except when I'm working out coordinates, and it doesn't usually get this complicated. In which case, we end up with n plus... and this ends up being k minus n. No, that doesn't look good. maybe it'll be okay still. Okay, so then it's n plus k. This is where, for some reason, this is where people who know maths come to torture themselves by watching me do elementary operations poorly. Okay, n minus n is nothing, so we get k. So, therefore, I think you'll find it's actually the same thing after all. Apart from where you can put this k on here. And then it's the same. Apart from not that there. That's not the same. It's actually it's got to go here. Because that was always on the outside, remember? That was always there. QED. Quadrant demonstrandum. Okay, what's chat saying? Climbot says induction is quite easy once you get your head around it. I don't miss writing out transfinite inductions up to the first uncountable ordinal though. Me either. That was tedious. It sounds tedious. And Stucky says, morning's going great. It's morning for you. Amazing. Happy morning. Or good morning. That's what people say, right? On Earth. You have a quiet day today, so it's going to be a lot of enjoying the math Twitchiverse. Oh, great. Amazing. Not that anyone asked, but I lift weights and I went to the gym this morning and I had a great time. I walked in and an impressive looking man came up to me and he said, K-Lack, of course you're here. Of course you're... No, he said, I've lost my phone. Could you ring it for me? Would you mind? And I said, of course. And I rang his phone and then he found it. And then he just chatted a bit. So, that was good. Inner Climbot says, torture's not right. Actually, it's quite satisfying as a teacher and not in a weird way to see that moment when someone starts to understand things for the first time. Yeah. That does. I can agree. I can agree with that. Missing a factor after the K, yeah. Oh yeah, the other K. Okay. Terrible. Oh, thunder. Oh yeah, oh my gosh. Convoluted way to get your phone number, true. Oh my gosh, I was playing. Oh my gosh. This is what this is what you were saying, isn't it? It's satisfying to see that when someone understands something. I don't think been played. This is just like the shutdown script again. No, I don't think that was it. He didn't seem like he was way out of my age bracket, and yeah, yeah. That wasn't the vibe, I think. Oh my gosh. All right. Okay, Bobbledon says you can apply inductive reasoning to weightlifting by proving you can lift 100 grams more yesterday than you could today than you could yesterday. I I hope to prove that one day, but not yet. I haven't proved it yet. I had a good session today, though. I don't get to talk about it very much. I say that I talk about it all the time, but I do love talking about weightlifting. I became a real gym rat over the past couple of years. And I would, does anyone want to speculate on what I was doing today? What my movements were today? Probably not. Dull conversation, but I just can't stop talking about it. Oh yeah, yeah, lift the universe, that's true. That would be pretty good. Where was I? Okay. Yeah, did that. I have to factor in death. Oh no. True. I have to prove that I can't die. Let's hope I can prove that as well. Okay, 15. How many 10-digit binary... Oh, it's a binary strings question again. How many 10-digit binary strings are there that do not have exactly 4 ones? Well, that'll be 1 minus... No, not 1 minus. That'll be the total number of binary strings, which will be 2 to the 10. 2 to 10. 2 to 10? 2 to the 10? 2 to 10. 2 to the power 10. 2 raised to the 10th ordinal? I don't know. 2 to the 10 minus those that do have exactly 4 ones, which we know how to do because I've had that drilled into me already. So that's 2 to the... This is lagging. I need to work on the performance of this Telestrator software I've built. Oh, terrible. Okay, 2 to the 10 minus... We've got 4 positions to put a 1. No, we've got 10 positions, and we want to choose 4 of them to flip, as somebody was saying earlier. Okay. Great. The computer scientist is sick of binary strings. I see how it is. Yeah, that's true. That's true, Bobbledon. I'm sick of binary strings. You know, I want to go back. Let's go back to the way things used to be. Let's go back to decimal computers. I'm sick of this binary nonsense. I want decimal computers. Let's go back to the... let me quickly Google this. I think one of the earliest... Yeah, ENIAC. Let's go back to the ENIAC. The ENIAC. If it was good enough for whoever was working on the ENIAC, it's good enough for me. Was it using the Manhattan Project? I think it... No, it wasn't. Maybe it was. Oh yeah, if it was good enough for the Manhattan Project, it's good enough for me. Let's go back to the electronic numerical integrator and computer. Actually, it's probably not. Let's not go back to that. But still. Still need to make that video about Leibniz's obsession with binary numbers. Leibniz? Okay. Hacker's Delight. One of the engineers I worked with last year introduced me to this book of bit twiddling tricks called Hacker's Delight. That sounds great. Drop the link in the chat if you have it. Okay. That's 15. We need to scroll down. It doesn't... Oh, phew. Okay. I thought there was more exercises. We're almost there. $17. How many... Oh... How many 10-digit binary strings haven't... No, wait, 17. How many 10-digit binary strings are there that have exactly 4 ones or exactly 5 ones? How many do not have exactly 4 ones or exactly 5 ones? Okay, well that seems trivial. I think. So if they have exactly 4 ones, well actually we don't need this if they have it. If they have exactly 4 ones or exactly 5 ones, then it should be 10 choose 4. Probably, maybe he's expecting us to calculate it out rather than just like lazily do this. Maybe that's why. I also do feel like this guy has a bit of a habit of putting the difficult questions in the middle. I've noticed that a couple times now. Minus this, I think. Amazing. Thanks for the link and a clone bottle. That sounds cool. Love to learn some binary bit twiddling tricks. I just can't handle that. That's too scruffy. I need to get my Apple Pencil hooked up to this thing. Oh, that's a good point. That's a good point, actually, Olidon. Is it the same? Okay, 17, 19. A 5-card poker hand is called a flush if all cards are the same suit. Suit is, yeah, clubs or whatever. How many different flushes are there? So in this case, we've got 13 cards in a suit. So it's going to be 13, the number of ways we can choose, 5 cards from 13 cards times 4, because there'll be 4 suits, right? It will be really awful studying maths, I feel, if you weren't familiar with like playing cards, or worse, if they were like illegal, because they're... I think some religions don't let you play with that stuff. I suppose you can still answer the same questions. I once dated someone who had I think she did play with playing cards, but I think she like maybe wasn't supposed to or something. Maybe I made that up. Okay, so 13. Choose 3.5, I think. Okay, great. Soon we will look at the answers, but I'm going to take a short break before we do that. So you get to listen to some rain sound. And I'll be back in a few minutes. I would love some of that sound outside right now. Back soon. Oh, it got really loud, did it? It's so loud, sorry. There's a part where it like gets really loud. No, it probably wasn't your fault. I noticed that Soding does this thing where he puts his tea on and then he comes back and chats while the tea is steeping. I think I'm going to try that today. So, anyone know any good jokes? It's probably because, Soding streams have like 1 billion viewers. So, any question? Any question, there's an immediate answer. How do you feel about the cover of compilers, principles, techniques, and tools? How do I feel about it? There's a bunch of them, right? So I think the old one with the red dragon. Yeah, the CGI one is my board is not competent enough to show this to you. But the new one freaks me out. The new one with the CGI dragon freaks me out. I like the red. I like the one where the dragon is green. The green dragon is good. The red dragon's a little aggressive. I don't feel like I think the whole point of it is that the book, the ideas in the book are supposed to help you slay the complexity of compiler design. But it feels to me like the one with the red dragon, he's not slaying anything. The dragon is in his computer. It's not right. Whereas the green dragon book, he's slaying that. He's slaying that 100%. Okay, this is the green dragon one. I'm gonna put a link to the green dragon one. That's the green dragon. And then if you don't know, I'll put a link into the red dragon as well. It's an Amazon link. Now, tell me the red dragon is being slain. That red dragon is in control. That red dragon has put his head into the computer. Now the green dragon is, he looks fraught. He looks like he knows that he's in danger. Maybe it's a different book. I think it's the same book, but I think the editions might be quite different. It does look actually kind of different now. I think they're in the same universe anyway. Yeah. So I'm feeling the green dragon's the one. Even though the green dragon I think is the most outdated. I'm very excited to at some point get to the point where we talk about the fact that Knuth did he did the LR he did a whole bunch of stuff in parsing. The LR parser, all that. He did a whole bunch of LR parsing that now people it was like, I think he got nerd sniped by better parsing. But now it's like it's not the I mean, I don't understand the work well enough to say, but people don't really use it as much. I think that's an interesting thing that he spent his time on that. Lexi T says, I'm currently reading the C programming book as well as some game engine development books for more performance work. That sounds cool. What are you working on? Oh, there's a question. Any advice for finding work in low-level systems? I spent 15 years in full stack. I want to pick up a job in the lower level, but I'm 12 years behind on low-level ability. Unfortunately, I have no advice. I have no advice on that question, other than stuff you would have thought of already, as I've not had a job in low level and don't actually know anyone who's done. I know. I've met people who did low level work. Deep knowledge of the language seems to be a common amongst them, but I don't know. I don't think I have any advice that I would say and know that you should trust me to give you good advice. Like, don't trust anything. I wouldn't trust me to give advice on that question, so I won't give any. But you have my support. That sounds like a brilliant path to go down, and just keep learning. That advice I do rate. Compiler theory, probably, yeah. Oh, you're looking at like low level like compiler theory stuff. Oh, that's cool. That's cool. Inner Climb Bottle seems to be a C hater, but do I have anything to say next? I don't think I do. C haters. Are we pro or against C in the chat? What do we say? Any vote? Anyone wanna vote pro C? In a Climb Bottle is a C hater. However, also can't open their marmalade. So clearly a modern language doesn't help with that. Doesn't help with everything. I was actually thinking of taking on a C project reasonably soon. Something significant, because I feel like I've just played around with it, but I'd like to build something more serious. No disguises. True. I read somewhere that you can basically write C in assembly macros if you're like really, if you want to like torture yourself, like that. But it's basically possible. I don't know if that's true or not, but it could be. Register keyword. Pleasing. You know, in the fourth community, they refer to all non-fourth languages as C, basically. To them, we're all C programmers, which is it's very funny. Like they'll refer to something as like C or a C programming stuff, and somebody will be like, oh no, that's not C, that's JavaScript. And they're like, well, that's C to us. Which makes sense. I mean, they kind of like fourth diverged from mainstream, let's say the mainstream programming culture before C or in contrast to C. Okay, I'll be back in a 2 minutes. 2 minutes. Okay, I've returned. Everyone's still friends, right? Nobody's falling out of a sea. Okay. Right, let's see how many I got wrong, shall we? Okay. 3.5. I don't want to use the find tool anymore. Heats my laptop up too much. My laptop needs a break. Lexity says there's been a civil war between pre-1997C and post-1997C. Huh. That sounds interesting. Okay. Right. Now, where were we? Uh, 3, 4, 8, 1, 3, 6. That seems right. And then 1, and then the thing in the middle. I'll give myself a... Come on. I'll give myself a tick for that. I didn't do 2, obviously. I did 3, so... A set has exactly 56. Okay, what do we get? 8. That one was a challenge. Thank you to everyone who helped me with that. 5. 16, choose 7. Great. Okay, what's this supposed to be? Choose, yeah, 10 choose 0 through 10 choose 3. Okay, great. 9. 360. That's yeah, 6 choose 2 by 4 factorial. Yeah, I think that's right. And then for 11, ten choose 3. Okay, fine. And then 13. Sorry, 13 is, well, I think it takes a similar approach to what I took. So I think I'm going to mark that roughly right. 15. Is FFmpeg still written in C? I was just wondering that actually. Is that still written in C? It seems like it should be. 2 to the 10 minus 10, choose 4. Okay, great. And then it's 17 is... yeah, that's right. And then 19 is... Yeah, I feel like they might use inline assembly in that. I feel like there's a lot of portability stuff that happens with FFmpeg for that reason. Okay. 13 choose 5. Yeah, so it's 4 times. Great. Okay. Let's call that a... Wow. Amazed I got those right. Those were kind of tough. Those were kind of tough for me. But that's the point of them. Right. Now we're going to learn about some sort of triangle now. I want to warn anyone who's afraid of triangles that there are some triangles in the next section. So be aware. Oh my gosh, okay, there they are. Yeah, we've got some triangles coming up. Okay, let me just cut into my terminal. No, actually that's gonna end everything. No, I won't do that. Let's see how much my laptop can take. Okay, watch out for the triangles. Check 94's got one of the great triangles out. Yeah. Okay, triangles. Let's go. Any thoughts on the new whiteboard setup? It's a little laggy. I want it to be smoother than that. Anyone got any thoughts? Do let me know. Still working on it actively. 3.6, Pascal's triangle and the binomial theorem. There are some beautiful and significant patterns in the numbers n choose k. We will now investigate a pattern based on one equation in particular. It happens that n plus 1 choose k is equal to n choose k minus 1 plus n choose k. Interesting. For any integers with n and k, with k between 1 and n. In a comment says the smoothing is a little aggressive, makes it hard to write small stuff. True, I need to fix that. Need to sort that out. Bubbledon says, instead of useful features, you should add a VTuber style face tracking so you can draw symbols on your face and they move with you. Now there you go. I could be a VTuber. I could meet my VTuber dreams. Maybe I am already. Maybe I am already. Chet94 says, do you prefer the curve smoothing? I wouldn't bother with it. I do prefer it because my fine motor control is not great. So I'm trying to work. I will improve it. I definitely will improve it, but I basically want something that makes it a little bit easier for me to write something relatively neat. This isn't quite working right now, but I feel like I'm in approximately the right direction. So, let me just, yeah. So if I then, one of the issues with this system is that currently smoothing is based on the number of points. So smoothing works in this library called Perfect Freehand by, I think it works by simplifying the number of points. Reducing the number of points, basically, which is fine. But what it means is if I do a fast movement, which will have few cursor points like this, it will simplify a lot. Whereas if I do slow but a similar movement, more points, less simplified. Now, I need to sort that out. It cares about speed, indeed. It cares about the number of points, which is caused by speed, or influenced by speed with a cursor. So I need to sort that out. But you should see my handwriting without any smoothing on. It's diabolical. Anyway, the point is, it should be clear. Oh gosh, okay. Yeah, need to sort that out. Need to get that fixed. Anyway, so I could have worked all this out, of course, before, but I thought I would test it live. Okay. Binomial stuff. Okay, for any integers. So this is kind of odd. Don't you think? It's kind of funny that that's the case. Let me try and think about that for a second. So if we have maybe it makes sense. It's probably going to be like a side of the triangle, right? That's probably what we're going to end up looking at. Interesting. Hmm. Okay, let's read on. To see why this is true, notice that the left-hand side n plus 1 choose k is the number of k element subsets of the set A is 0 through n, which has n plus 1 elements. That's acting as a filter, right? Notice that the left-hand side, n plus 1 choose k, is the number of k element subsets of the set A, where A is the set of the numbers symbols 0 through n, which has n plus 1 elements. Such a subset either contains 0 or it does not. The n choose k minus 1 on the right is the number of k element subsets of A that contain 0, because to make such a subset, we can start with 0 and append it an additional k minus 1 numbers selected from 1, 2, 3 through n. And there are n choose k minus 1 ways to do this. Also, the n choose k on the right is the number of subsets of A that do not contain 0. For it is the number of ways to select k elements from... Okay. In the light of all of this, equation 3.3 just states the obvious fact: the number of k element subsets of A equals the number of k element subsets that contain 0 plus the number of k element subsets that do not contain 0. Equation 3.3 just states the obvious fact that the number of k element subsets of A equals the number of k element subsets that contain 0, which will be... now, what is the number of k element subsets that contain 0? This. And that's true because we're taking away one element, which will be 0, and 0 is the same as anything else, so... Fine. Plus the number of k element subsets that do... 0 is only special here. 0 is only special because it's the only one that's guaranteed to be in this sequence. Provided that it's above... Provided that we're in some sensible range. Because, 3 might not be in there. It might not be large enough. Okay. K element subsets that contain 0 plus the number of k element subsets that do not contain 0. And that is this part. This is the ones that don't contain 0. It's the ones that don't contain 0 because we've taken n down by 1, essentially. So we've removed one of the symbols, really, that we can choose. Well, actually, both of these remove one of the symbols. This removes... Yeah, okay. Weird. Fine. Okay. Having seen why equation 3.3 is true, we now highlight it by arranging the numbers. Okay, let me get rid of that. Arranging the numbers n, choose k in a triangular pattern. The left-hand side of figure 3.3 shows the numbers. Just scroll down again. Shows the numbers n, choose k arranged in a pyramid with 0, 0 at the apex. Just above a row containing 1, choose k with k0 and k1. Below this is a row listing the values of k, 2 choose k, for k is 1, 0, 1, 2, and so on. Dexter, I have no commands active, but you could tell me whatever specs is supposed to do, and I could tell you. They both remove 0 as a choice because you've already made the choice. Both of them remove 0. It is just a matter of picking elements, either k or k minus 1 elements from what remains. K lacks math. K lacks commands, that's true. That's true, unfortunately. Amateur hour here. Okay. This triangle's just for illustration, I guess. Oh no, this is the count. This is the counts. This is the result of n choose. Like 2 choose 1 is 2. Fine. Now, this is that equation, right? But we know that's I already know that's how Pascal's triangle works, right? So in this picture, this is the number of ones, the number of, yeah, so this is the number of ones. 2 choose 0 and 2 choose 1. Okay, where does this come in? Yeah, so, yeah. So, I'll keep saying so until it makes sense. Always a good, yeah, so n choose k is on the right is the number of subsets of A that do not contain 0. So, this is the number of ones that don't contain 0, and this is the number of ones that does contain 0? Do contain 0? I guess, maybe. Okay. Any number n plus 1 choose k for 0 within k and n exclusive in this pyramid is just below and between the two numbers n choose k minus 1 and then choose k in the previous row. But equation 3.3 says n plus 1 choose k is equal to n choose k minus 1 and then choose k. Therefore, any number other than 1 in the pyramid is the sum of two numbers, the two numbers immediately above it. Okay? This pattern is especially evident on the right of figure 3.3, where n choose k is worked out. Notice how 21 is the sum of the numbers 6 and 15 above it. Similarly, 5 is the sum of the 1 and 4 above it, and so on. This arrangement is called Pascal's triangle after, I think it's Blaise Pascal. Correct me if I'm wrong. 1623 to 1662. A French philosopher and mathematician who discovered many of its properties. We've shown only the first 8 rows, but the triangle extends downward forever. The triangle extends downward forever. We can always add a new row at the bottom by placing a 1 at each end and obtaining each remaining number by adding the two numbers above its position. Doing this in figure 3.3, which I guess would be on the right if this was a real book, gives a new bottom row. Oh, in the right, sorry, the right triangle. This row consists of the numbers 8 choose k for k between 0 and 8, inclusive when we've computed them without the formula 8 choose k at all. Any n choose k can be computed in this way. The very top row, containing only 1 of Pascal's triangle, is called row 0. Row 1 is the next down, followed by row 2 and row 3. What comes after that, though? It's kind of weird. He doesn't explain what comes next. Thus, row n lists the numbers n choose k for, exercises 3, 5, 13 and 3, 5, 14 established this for each, In other words, the kth entry of row n of Pascal's triangle equals the n minus kth entry. In other words, the kth entry of row n in Pascal's triangle equals the n minus kth entry. Oh, so it's symmetrical. This means that Pascal's triangle is... Okay, so just read ahead. Don't bother thinking. With respect to the vertical line through its apex, as evidence in figure 3.3. And then we've got some interesting... We've got some interesting things there. Notice that row n appears to be a list of the coefficients of x plus y to the power n. Row n appears to be a list of the coefficients of x plus y to the n. For example, what? What is he talking about? Is this in any way related to anything? Probably. Just keep reading, try and understand it, okay? For example, x plus y squared equals 1x squared plus 2xy plus y squared. Right, okay. Okay, wait. Let's just zoom in on this so we can understand it a bit better. Right, so this is one formula, not a bunch of formulas. Okay, that makes more sense. Right, and this evaluates to something. It evaluates to x plus y to the power n. Right, so this would be an expansion of this. Is that right? Yeah. Yeah. Okay. Fine. Well, that's cool. Thank you, Isaac Newton. Is that ring in the background chirping of that common insect? Let's turn it up. There is a little... It's still there if I mute myself. I think it's in the sound. I don't think it's in real life for me. Probably something like that. Posture check myself. Thanks, Sam. You can listen to it yourself. Somebody asked the asked the sound, the other stream. I can't remember where it is now. Let me see if I can find it again. Every day I forget the sound. Still forget it. It's on Freesound anyway. Okay, so there's a triangle. Yeah. In fact, this turns out to be true for every n. This fact is known as the binomial theorem, and it is worth mentioning here. It tells us how to raise a binomial x plus y to a non-negative integer power n. Theorem 3.1, the binomial theorem. If n is a non-negative integer, then x plus y to the nth power is equal to n choose 0, xn, n choose 0, n minus 1, yeah. Okay, y, okay, right. And then fine. For now, we will be content to accept the binomial theorem without proof. You'll be asked to prove it in an exercise in chapter 10. Oh, good. You may find it useful from time to time. For instance, you can use it if you ever need to expand an expression such as x plus y to the power 7. To do this, look at row 7 of Pascal's triangle in figure 3.3 and apply the binomial theorem to get this. Goody. Wow, that looks horrendous. Hello, Atom Fighter. How you doing? How's the fight against those atoms doing? You managed to cut any in half yet? They say you can't do that. I know different. This is why the numbers n choose k are also called binomial coefficients. Huh. Thank you for the information, Bobadon. Yeah, Atom Fighter may be splitting atoms in... Oh, you fight for the atoms, not against them. Oh, I see. Well, don't we all? I suppose some maybe fight against them. Maybe there's an antimatter version of us out there. Does antimatter life exist in the universe? Discuss. Okay, write out row 11 of Pascal's triangle. This guy's a real joker. Okay, row 11. It's going to be it's going to be like 0, choose 11, right? Zero, choose 11. 1, choose 11. 2, choose 11. 3, choose 11. 4, choose 11. 5, choose 11. 6, choose 11. 7, choose 11. 8, choose 11. 9, choose 11. 10, choose 11. 11, choose 11. There, that's the answer. Use the binomial theorem to find the coefficient of x to the power 8 in... Okay, can I do this without doing like a million years of work? Let's hope. Okay, so it's expanding. Yeah, okay, so we're saying x is x is x, and y equals 2. And so if it's the coefficient of x8, well, so this is row 5, right? We've got a x5, x4, x3, x2, x1, x0. So we want to be in row 13. Let me write this down. We want to be in row 13. That's a terrible 3, sorry. Right, slower. We want to be in row 13, and we want to be... So this is choose... sorry. So this one is x5 because we're on the first row. So we want to be in term 13 minus... I'm just being lazy here. I'm just being lazy about it. 13 minus... yeah, so 30 minus 5. Hello, Ndeka. How are you doing? Yeah. Okay, so I think it's probably going to be 13 choose... 13 choose 5, maybe? Sorry, you've come to the wrong stream if you don't want to see maths. Good to have you here, but the maths there's a very math heavy stream at the moment. It won't be forever. Okay. So yeah. "13 choose 5. I really don't. I'm getting tired. That's what's happening. 13 over... math factorial 5 multiplied by 13 minus 5 1287. Why am I even doing this? Why am I doing this again? Yeah, that's the coefficient, right? If I've got that right, and there are several steps that I could have made it like an off by 1 or like a subtracted the wrong number. The kth entry of row n of Pascal's triangle. So the kth entry of row n of Pascal's triangle, yeah, actually ends up being, yeah, the coefficients here. And then we start off at 5, and we start off at 13, and we try to get to 8. So we end up with the fifth being our k, or the fifth being our k, and 13 being yeah, okay. I've accidentally started some sort of conceptual debate about antimatter versus matter in the chat. I apologize. It's like InfoWars in here, but for random random questions. Hello, it's really Ran. Only ever done math while cramming for exams, says Sam. Yeah, I mean, I've done a little bit of math for programming purposes, but not very much. But you know, I'm doing it for content now, so I've got good motivation. Is the mathing today? It firmly is. It firmly is. Yeah. It's definitely mathing today. The maths is beating me today. It's beating my ass. If I was American, I might say that. How's your day going? It's really Ren. It's getting rain. Getting rainy. And Decker is saying, hopefully you can hear me over the rain. Is this the math that's used to make animations like those in Reels and motion graphics? Maybe. You know, it reminds me though, the reason I picked up on that is it reminds me they, you know, 3 Blue 1 Brown has the whole Manim, like a video engine type thing, mass visualization engine. Well, I watched this video the other day. I can't remember who it was by. Apparently, they've AI'd him. They're doing AI 3 Blue 1 Brown now. Somebody's downloaded Manim and they've gotten an AI to write all the scripts. And they're just generating 3 Blue 1 Brown style videos and putting them on YouTube, and they're all terrible, basically. But then in the comments of this video, they were saying, I don't really care if they're terrible as long as they're right, which I guess if you want to consume your facts about mathematics through the least efficient mechanism possible, which is a random, like a YouTube video where an AI has written some Manim code, I guess you could do that. I mean, why not? You know, why not? I shouldn't judge. If that's what they like, then great. But it's funny because, you know, if you're 3 Blue 1 Brown, you're probably feeling like you've created some You had some your invention of this mathematics visualization library has really had some unintended consequences. Three artificial, one intelligent. That's good. That's good. It's really Ren says, I believe from your accent that you're from the UK too. Yes, and the country in the last few days has been on fire. Is the rain an audio track or IRL from the window? It's an audio track. I've posted the link before. It's pretty good. It has one moment where it gets extremely loud suddenly, just for laughs. It's interesting at the moment with AI and making videos, because the last video I properly produced, the idea you'd get like some sort of like realistic AI video was nonsense, and now it's reality, and so I'm thinking I might develop like an AI colophon. Is that how you pronounce that? Because, you know, when I'm writing code, I use like AI autocomplete and stuff like that. So I can't really say no generative AI was used entirely in the production of this project. Some projects I can, but you know, it's 2026. Occasionally, I will consult, or I will get autocomplete running or something like that. But it's different, obviously, from, you know, just wow, my keying is terrible today, awful. Different from like getting the AI to make the video. So it'd be nice to have some sort of proper disclosure there that was honest. Dexter says it's summer here and we're melting. We're melting in the US, I guess, alive. My skin get burns from the sun easily in 2 hours. Oh, terrible. Yeah, this is we're just pretending that there's rain in this channel. Decker says, isn't it better that everyone can make AI slop, so the internet will be filled with AI videos and then it becomes normal, which will make human-made more valuable? And it's really when it says, I believe that a lot of the videos that 3 Blue 1 Brown put out are so popular because you can tell. I feel like I'm going to shout over the rain now. Let me turn this down just a little bit, because you can tell how enthusiastic he is about the subject. A lot of the times the enthusiasm can be felt through the metaphors and comparisons people use to explain a topic. I don't feel that AI could add the same special sauce to a math-related vid. Yeah, it's interesting. It's an interesting time. So one of the reasons that so I have a rule, which is every video that I make, I have my face in it. Like every video I have my face in it. And partly because of the way that I went about this was I kind of saw where AI was going, and I think a lot of like there is a way in which you can look at things like YouTube or even Twitch and say it's simplistically you are producing a resource, content, entertainment content of some kind that you are then delivering through a platform to a person, and it doesn't really doesn't really matter like how that content is produced. But I think that, you know, particularly this comes out of my experience in education, like you can get correct information quite easily. Like correct information has been out there for a long time on most every topic you need to learn. And now we have it in an easily digestible form through AI, but a lot of education only works if you have a human relationship with another person. And there are different ways to have a human relationship. Like if you're a direct teacher, you have a relationship with your students, and likewise. It's not the same as being friends, but it's still a relationship, and it's useful to do work with. And I think now also, like with content, the relationship, although again it's a very different relationship than knowing people like in person, it makes a difference to what you're doing. Okay, chat is saying some interesting stuff. Started to become distrustful of videos where the narrator doesn't show their face. Yeah, me too, in a Klein bottle. It's a lot of even where people use their voices, like sometimes you can tell the script is AI generated as well. I actually I made an OBS plugin using AI the other day, which turned out all right. I'm not using it right now, but yeah. Anyway, these exercises, huh? Okay, 3. Let me push through these. Use the binomial theorem to show that the sum. Oh gosh. Okay, where did I go? What did I do? I just clicked something. I just went to a completely different place. Okay, all right. I clicked something. Never click. That's the lesson. Never click if you can avoid it. Okay, here we are again. Okay, apparently if you click that, it goes somewhere else. Use the binomial theorem to show that the sum of, I think that's sum of, I don't even know that notation now. The sum of all the elements ranging between from k equals 0 through n, maybe? N choose k is 2 to the n. Does anyone know what this notation here is asking for? I actually don't know. Yeah, recall would be nice. If I could recall it, that would be great. Summation. So it's summation from k to. What is the k and n indicated here? I know this is like basic stuff. K equals 0 to k equals n. Right. Okay. Thank you. Yeah. K equals 0 to k equals n. Yeah, I didn't have it before. Desert ambience. Okay, maybe next time. Okay, desert ambience next time. I'll have a dry ambience next time. Maybe it's hard to get dry ambience actually. Maybe like windswept, lots of wind. Wow, the keying is diabolical today. Just looks awful. We need to get like yeah. Anyway, we won't even talk about keying today. Keying is. Yeah, I need to change that. I do need to change the audio track actually. It's getting a little old. I'm tired of all this rain. Getting samey. Bring back all that horrible scraping sound we had a few weeks back. Oof, that was rough. That was really rough. Okay, let me write this out. Okay. Can you tell I've never even written this symbol before? It's so big. What? Okay. Wow, this is really lagging now. Okay, then and choose K. Right. And this is supposed to then end up equaling 2 to the power n. Tall sigma. Okay. Apparently this is a good exercise. Alright, I'm going to lock in. I'm going to lock in and try it out. Right. Use the binomial theorem to show this. Now, what's the binomial theorem again? Binomial theorem. This, right. Is that the binomial theorem? No, that's Pascal. That's not the binomial theorem. Oh, why have I just forgotten what the binomial theorem is? Terrible. Okay. Right, it's this. It's this. That's what we're going to use somehow. What? Try writing the right-hand side with the sigma summation notation. Okay, let's try that. So well, let me start writing, maybe something will come to me. Nope. Now we want to express this as a summation, do we? In the binomial theorem. Oh, right, sorry. Okay. Right. Okay, the right hand side with this with the summation. Okay, well we have sums in that at least, so that would kind of make sense. So we're gonna then, well, let's try it. So we'll have k being 0. No, wait. N choose k, maybe? Yeah. Because then we're, no, we just write the sequence. Just write the sequence. So yeah, you know what? I'm being slightly led. So let's say we've got like this could also be 2 plus 0 n. Which would be so y is always going to be 0 for all of the terms other than right. Okay. So if we've got this, which is the same as this, then all of the terms other than the first one will end up being 0. So we end up with n0 x n. I really thought I was going somewhere with that. What is x? True. X is 2. True. And then n choose 0 is going to be 1. Because there's only one, it'll be the empty set. So we get this. Again. Doesn't necessarily help us show that these two are equal, though. Everyone's reassuring me, which is it give me the indication I'm on the wrong track. Okay, these two are equivalent. This is equivalent to this. Is there some sort of chain here? Okay, so we've got nope. Yeah. Okay, so we've got these two connected. And we've got these two connected. But how does it connect to this? Check 94 says, you chose 2 equals 2 plus 0 and simplified the binomial theorem enormously. Perhaps you can simplify it in another way. That's true. We've not touched proofs yet in this book. It's really random. It's probably this is probably designed to create in my mind the desire to learn proofs. But we haven't. We're in the chapter just before we get to proving things in this book. Okay, so we could have 1 plus 1 to the n. This would then get us we'd then be able to expand it but n to the 1 is always going to be 1, right? So, oh, I see it. That's pleasing. Okay. So I think, so the idea then is, if you look at this here, right? We're going to have n minus x to the n, x to the n minus 1, y squared, etc. But all of those are going to end up being 1 because anything to the power, sorry, 1 to the power anything is going to be 1, and 1 to the power anything is going to be 1. So we're going to end up with these terms here. All of these will end up being 1. And so we're left with this part of every term. And this part goes, in theory, it goes from zero to n, which is the range we're supposed to be calculating this within. So that's the line, right? Thank you, Check94, for that. That was don't think I would have gotten anywhere close to it without that. Yeah. So this expands to basically, I really need to get my Apple Pencil going on this, but n0 plus n1 plus all the way through to it is n, isn't it? N, and then this will be, what will this be? Yeah, n minus 1, right? Yeah, n minus 1. Plus n choose n. Which is equivalent to this thing. All of these summed up. Okay, interesting. Avalon says, what happens where you interpret this equality about numbers of subsets of certain sizes? Something. We've seen this loads before. This is the binary strings thing. Conditions around show prove are usually constrained to the point of eliminating any difference between those terms in most questions. Yeah, so it's a show, I suppose. Yeah, I don't know. This book hasn't taught me anything about proving things yet, so it would be surprising if it asked me to prove anything. Okay. Seven. More things. More showing. Probably if I did the even number questions, this would be easier. Okay. How much do I want to work through the rest of these? Really recommend doing 366 as well. We've only been streaming three and a quarter hours. It's not hardly time to finish yet. Okay, use definition 3.2 on page 85. And fact 1.3 on page 13 to show those two things. Right, so we're using some different facts, but we're showing the same thing. Okay, so fact 3.2, we're on page 92. Okay. 3.2, if n and k are integers, then n choose k denotes the number of subsets that can be made by choosing k elements from an n element set. Yeah, my brain is in no shape for this, as much as I would like it to be. Where were we on? Where are we on? Oh, we're on a completely different. Okay, let me return to these exercises next time. I'm just gonna scroll through the next one, and then we'll see how I'm feeling about those exercises. Where's my highlighter? There we go. Okay, we'll come back to those next time. Inclusion-exclusion principle. Many counting problems involve computing the cardinality of a union B of two finite sets. Okay, we examine this kind of problem now. First, we develop a formula for cardinality of A union B. It's tempting to say that A union B must equal, yeah, but that's not right, because there might be some overlap. We might do some double counting. Yeah, so, right, so therefore, the cardinality of A plus the cardinality of B exceeds A union B by A intersection B. That's interesting. And consequently, cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of A intersection B. Interesting. I feel like I've seen that before somewhere else. Notice that sets A, B, and A intersection B are all generally smaller than A union B, generally. So fact 3.6 has the potential of reducing the problem determining A union B to 3 simpler counting problems. It is called the inclusion-exclusion formula because elements in A intersection B are included twice in A plus B, then excluded. Yeah, fine. Notice that if A intersection B is an empty set, then we do in fact get this thing. This is the instance of the additional principle. Makes sense? Conversely, if A union B is equal to cardinality of A plus cardinality of B, then it must be A intersection B. No, it must be that this is an empty set. Okay, fine. We've got some examples here. A 3-card hand is dealt off of a standard 52-card deck. How many different such hands are there for which all 3 cards are red or all 3 cards are face cards? Okay, so that's where there's going to be some intersection going on. So let me see if I can puzzle this one a little bit first before moving on. How's my computer temperature doing? One second. Okay. Oof. All of this. Let's get rid of that over there. Okay. Yeah, anyway, what was I doing? Yeah, okay. So if we can compute the cardinality of 3 cards being red, all 3 cards are red or all 3 cards are face cards. So that will be... Oh, that's the wrong place. That will be... Let's say the first one is R. That's going to be the number of red hands we can produce. That's 26. Choose 3, maybe? I think. And then face cards. Now, how many face cards are there? There's king. Does ace count? No. King, queen, and jack. So that's 3 out of every 13. Or rather, it's just 4 threes. It's 12. So that's 12. Oops. 12, choose 3. And then we need to somehow compute the number of all red hands that are also all face cards. Now all red hands that can be all face cards. Now there's, how many cards is that? There's 6, right? So that'll be, no, that'll be 6, choose 3. And so we end up, you know, taking this, adding this, and subtracting this, I think. Let's see whether it adds up the same way. Let A be the set of 3 card hands where all 3 cards are red. Let B be the set of 3 card hands in which all 3 cards are face cards, J, a jack, king, or queen of any suit. These sets are illustrated below. We seek the number of 3 card hands that are all red, or all face cards, and this number is... Sorry, I messed up. Did I mess up? No, I didn't. We seek the number of... Yeah, in the union, yeah. So then we add these and we take the intersection and we subtract that. We examine these separately. Any hand in A is formed by selecting 3 cards from 26 red cards. We got that one. Similarly, any hand in B is formed by selecting 3 cards from the 12 face cards in the deck. So 12, choose 3. And that's 6, choose 3. Okay, good. Now we can answer our question. It's that many. Cool, okay. A 3-card hand is dealt off a standard 52-card deck. How many different such hands are there for which it is not the case that all 3 cards are red, or all 3 cards are face cards? So here, how many different such hands are there for which it is not the case that all 3 cards are red, or all 3 cards are face cards? So we want to all the possible 3-card hands that are not all red and not all face cards. Right, so the problem here is if we end up trying to compute separately the number of cards, the number of hands that are all red and the number of hands that are all face cards, and then subtract those to get the number of all non-red hands and all non-red face cards, and then add those together or something, then we're gonna end up double counting, because there'll be some hands which are both not red and not face cards. Interesting. Okay. We'll use the subtraction principle combined with our answer to 3.17 above. The total number of 3-card hands is that. Fine. To get our answer, we must subtract from this number the number of 3-card hands that are all red or all face cards. That is, we must subtract the answer from example 3.17. Okay, fine. This is an analog of fact 3.6 that involves 3 sets. Consider 3 sets A, B, and C as represented in the following Venn diagram. Using the same kind of reasoning that resulted in fact 3.6, you can convince yourself that A union B union C is the same thing as A plus B plus C minus A union B, which is this, minus... Sorry, A intersection B, which is this, A intersection C, which is this, A intersection C, sorry, B intersection C, which is this, plus this center section here, this one. There's probably not much harm in ignoring this one for now, but if you find this kind of thing intriguing, you should definitely take a course in combinatorics, which it's really ran as I think saying. Ask your instructor. I've got no one to ask. Okay. I am not going to do all those. What comes after this? Multi-sets. And then it's division and pigeonhole principles. And then it's combinatorial proof. And then I think we're done with counting. Wow, that's been pretty awkward. Okay, I think I'm going to call it a day there. Slightly shorter stream than I anticipated, but I think I can't force my brain to do anything it doesn't want to do. I don't have anything else obvious to do, I don't think. I don't think so. I'd have to ask myself, yeah, I would. Thanks, Wobblodon. I appreciate that. I appreciate all the support in chat as well. It is, learning is difficult. Knowing stuff already is great. Knowing stuff's great, learning is difficult. But that's why, that's that. It's really when you had a question, you had a point about the National Lottery. There was actually an exercise earlier which asked, I think, exactly that. Let me see if I can find that exercise. I think I might have done it. Maybe it was in today's stream. No, that was last stream. It's raining again. Or maybe it was an example. There was something. Oh yeah. But with 36 balls. You have to write your thesis, Bob. Oh no. I'm sorry. That sucks. Don't you could just tell us all about it, Bobbledon, if you like. I know people who are writing a thesis love to talk about it, right? What's your favourite question at parties? What's your thesis on? Thanks for hanging out, Sam. Have a good rest of your day. Okay. Now, what are we thinking? What are we thinking raid-wise now? Who's online? Bye, Lazy Schemer. Hi, Lazy Schemer. Hi, bye, Lazy Schemer. A lot of vibe coders online. People are vibe coding. But we won't... we'll try to avoid that. Somebody who looks cool is streaming in Polish, but I guess it's a bit of a faux pas to just raid a Polish stream. Because none of you'll be able to understand it, unless you're Polish, in which case you will. Is there a math category? There's a math, I think there's a math tag. Oh wow, there is a category. That's wild. I guess I should be in that. Whoa, I didn't even know this existed. Wow, they're all doing it on paper and everything. Wow. Okay, all right, let's check this out. All right, we're gonna go and raid somebody. Wow, this person's wearing a tie. That's how you know it's gonna be good. All right, we got 10, 9, 8, 7, 6, 5, 4, 3, 2. Have a good day, everyone. Laters.